Hi, this is part two of matrix operations. Well, just as we had mentioned, just as we learned with vectors, we define equality between vectors, we define addition between column vectors, and then scalar multiplication among column vectors. So we're kind of doing a similar thing here with matrices, even though for matrices, they are not completely new to us. Remember when we were talking about things that are noted like this alpha R sub j, right? So it could be 5 R sub 3 or something like that. And we would write this on top of an arrow. This is in the process of computing the RREF of matrix, the reduced row echelon form. So for that scenario, we were already doing operations on a matrix, operation on matrices, and specifically on rows of a given matrix. Okay, so back then we would say a scalar multiplied by a row, and that meant that that operation was like a distributivity, an application of distributivity, because that operation implied that we would multiply every single element of that row, every number in every location of that row would be multiplied by a scalar. So now we're going to extend that idea to multiply not just by one specific row, but instead by an entire two-dimensional array, all the rows and columns, all the numbers of the matrix will be then multiplied by a scalar here denoted as alpha. So the formal definition reads as follows. Suppose that we have a rectangular, suppose we have a rectangle here that we're calling A, and this is the matrix A, and that we have a scalar, that would be a little dot here, scalar alpha, assumed to be a complex number. Then the matrix denoted here as alpha A, this would be a new matrix, is defined as follows. The ij entry of alpha A is no other thing than multiplying two complex numbers. That would be alpha multiplying the ij entry of the matrix. Okay, so this basically means that we propagate that multiplication throughout. So here's the example. This matrix has 3 rows, 2 columns, and we're going to multiply that by the scalar 7. 7 is a complex number with 0 imaginary part, and so multiplying the new matrix alpha A is a matrix that results by multiplying the scalar times the matrix, but that means that we're basically multiplying every single entry of that matrix by that one scalar, right? And this is going to give 14 on a row 1, column 1, and so on, right? So that's how these numbers here result, this number on row 1, column 2, this number results from multiplying the scalar times the entry that was previously located in that location, right? And so on and so forth. So matrices, just like vectors, are going to using the definitions on scalar multiplication, addition, and the definition of equality between matrices, we can then establish that the set of matrices M sub Mn is a set that, using the addition among matrices and using scalar multiplication, will satisfy the following properties. All these properties, they look very similar to the properties we had learned before from vectors. The first property has to do with closure. If you add two matrices already members of this set M sub Mn, the new matrix A plus B is also a member. It's inside that set. It doesn't leave the set. So in that sense, the first property here has to do with what we call mathematics closure. Okay, that operation, this operation, addition of matrices, is closed, or the set is closed under addition. Scalar multiplication also has that closure property. Things still remain within the set um, formally speaking, this set of matrices, the set of all rectangles, this is going to have a fancy name, okay, that we will explore in more detail later. And that fancy name is vector space. But you say, but this is a set of matrices. Well, that's why later vector, the word vector, will be used in a more abstract, more theoretical sense. But the good thing is to keep in mind that scalar multiplication of matrices, that operation is also closed. Is the set of all rectangles is closed under scalar multiplication. Addition is very intuitive. We had established that, look, if you want to add two matrices, they do have to satisfy that they need to have the same number of rows, same number of columns. So certainly if you're adding them up, here is A and here is B, they have the same number of rows, same number of columns, then you may proceed. Addition is cool, and it's cool also because it inherits properties from complex numbers. And at the level of complex numbers, if you had A sub I j and you're adding that to B sub I j, because each of these is a complex number due to commutativity of addition of complex numbers, that sum is the same as if you add B sub ij first to A sub ij. And this property of commutativity of complex numbers implies that the matrices, when considering addition of matrices, they are addition of matrices is commutative. Okay, it commutes. It is possible to have the commutativity on the addition of matrices. That's what this property is about. The next property has to do with carrying out the operation without swapping or changing the order of how things enter into the operation or the operator. This property is about grouping and carrying out the operation in some groups first. Here you can see in both sides of the equal sign we have always A, B, and C, A, B, and C in that order. The order doesn't change, but this means that if we choose to group B, to add B plus C first, okay, we do B plus C first, that gives us a new matrix, and then second we add A plus the new matrix, the new obtained from B plus C. That gives us a matrix, which is the same as if we first add A plus B, okay, add first A plus B, that gives you a new matrix, and then add the new matrix to the matrix C. You obtain another matrix, and you will see that the latter would match the formula, okay, and that's what this property is about. So we have talked about properties very similar to these properties listed here, but in the context of vectors, we did talk about that before. Now they're referring to the vector space of matrices with m rows and n columns. There is a matrix that contains all entries equal to 0, and one of the good things about the 0 matrix is that when you pass the 0 matrix as an argument for addition, in other words, if you add the 0 matrix to another matrix, that is not going to change anything on the other matrix. So adding the 0 matrix to an existing matrix A equals A. The entries of A remain unchanged. Under addition, that is, every matrix has another matrix that is considered the inverse of that matrix under the addition operator. That only means that in terms of adding matrices, if you add the entries of this new matrix here denoted as minus A, that entry will cancel in terms of addition the entry of the existing entry on the matrix A. Okay, it would yield a 0, that canceling in that sense. And so the other properties listed here involve scalar multiplication. There is associativity there. Again, you have alpha, beta, and the matrix A. Alpha and beta are considered complex numbers. They're scalars. So it's not about changing, switching the order in which alpha and beta appear here. It's more about carrying out one operation first. So this here is perform or carry out this scalar matrix multiplication first and then multiply scalar alpha to the new matrix, while here the group is carry out the scalar multiplication to obtain a new scalar, and then take that scalar and multiply it by the matrix. You will see that indeed both of these things are equal to the same matrix. Okay, and then there are properties here involving scalar multiplication and addition of matrices, or addition of scalars and then scalar matrix multiplication. So all these properties, we will see this in more detail, are super important to establish that in fact this set is what we consider a vector space. Okay, space is a set, but here you will see how vector space is a set with important properties.